Up to now, we have seen the most important scanning types to discover a network. There are some other scanning techniques in Nmap which are not used as much as the others, but in some cases, you may need to find some other ways to be able to discover the sensitive hosts in a network. In this slide, we'll see 3 more scan types: null, fin, and Christmas scans. The common ground of these 3 scanning methods, null, fin, and Christmas scans, is that they send packets to the target systems in which SYN, ACK, and wrist flags are not set. Null scan, N, does not set any bits. That is, the TCP flag header is 0. Fin scan, F, sets just the TCP fin bit. Christmas scan, X, sets the fin, push, and urge flags, lighting the packet up like a Christmas tree. There are 2 rules defined in RFC standards about such packets. The first rule is, if the destination port state is closed, an incoming segment not containing a wrist causes a wrist to be sent in response. The second rule is, packets sent to open ports without the SYN, wrist, or ACK bits set are dropped. These 3 scan types are exactly the same in behavior except for the TCP flag set in probe packets. If a wrist packet is received, the port is considered closed, while no response means it is open or filtered. If an ICMP unreachable error, type 3, code 0, 1, 2, 3, 9, 10, or 13 is received, the port is marked as filtered. So as a result, with these types of scans, you can find out if a port is closed or not. It's not possible to understand if it's open or filtered if there's no response. This scan is different than the others discussed so far in that it never determines open or even open filtered ports. It's used to map out firewall rule sets, determining whether they are stateful or not and which ports are filtered. The ACK scan probe packet has only the ACK flag set. When scanning unfiltered systems, open and closed ports will both return a wrist packet. Nmap then labels them as unfiltered, meaning that they are reachable by the ACK packet, but whether or not they're open or closed is undetermined. Ports that don't respond or send certain ICMP error messages back, type 3, code 0, 1, 2, 3, 9, 10, or 13, are labeled filtered. Idle scan is an advanced scan method that allows for a truly blind TCP port scan of the target. Truly blind TCP port scan means no packets are sent to the target from your real IP address. Instead, a unique side-channel attack exploits predictable IP fragmentation ID sequence generation on the zombie host to gather information about the open ports on the target. IDS systems will display the scan as coming from the zombie machine you specify. The idle scan is based on the following 3 facts. As you already know, one way to determine whether a TCP port is open is to send a SYN packet to the port. The target machine will respond with a SYN ACK packet if the port is open, and wrist if the port is closed. A machine that receives an unexpected SYN ACK packet will respond with a wrist. An unexpected wrist will be ignored. Every IP packet on the Internet has a fragment identification number, IP-ID. Since many operating systems simply increment this number for each packet they send, probing for the IP-ID can tell an attacker how many packets have been sent since the last probe. So first, let's see what happens in an idle scan if the target port is open. The first step is to probe the IP-ID of the zombie system. The attacker sends a SYN ACK to the zombie. Since the zombie does not expect the packet, it sends back a wrist with an IP-ID. The second step is to forge a SYN packet from the zombie to the target system. The target sends a SYN ACK in response to the SYN that appears to come from the zombie. Since the zombie does not expect the packet, it sends back a wrist, and so it increments its IP-ID in the process. Third step is to probe the zombie's IP-ID again. The attacker sends a SYNAC to the zombie again. The wrist packet of the zombie has an IP ID, which is increased by 2 since the first step, so the port is open. Now let's see what happens in an idle scan if the target port is closed. The first step is to probe the IP ID of the zombie system. The attacker sends a SYNAC to the zombie. Since the zombie does not expect the packet, it sends back a wrist with an IP ID. The second step is to forge a SYN packet from the zombie to the target system. The target sends a wrist because the port is closed in response to the SYN that appears to come from the zombie. The zombie ignores the unexpected wrist, so its IP ID does not change. Third step is to probe the zombie's IP ID again. The attacker sends a SYNAC to the zombie again. The wrist packet of the zombie has an IP ID which is increased by only 1 since the first step, so the port is not open. You follow? So then, here's the last one. Let's see what happens in an idle scan if the target port is filtered. The first step is to probe the IP ID of the zombie system. The attacker sends a SYNAC to the zombie. Since the zombie does not expect the packet, it sends back a wrist with an IP ID. The second step is to forge a SYN packet from the zombie to the target system. The target, filtering its port, ignores the SYN that appears to come from the zombie. The zombie is unaware that anything happened, so its IP ID remains the same. Third step is to probe the zombie's IP ID again. The attacker sends a SYNAC to the zombie again. The wrist packet of the zombie has an IP ID which is increased by only 1 since the first step, so the port is not open. So from the attacker's point of view, the filtered port is indistinguishable from a closed port. Do you see why? In both cases, the IP ID is increased by only 1. So let's have an idle scan. To be able to perform an idle scan, we first need to have a zombie computer on the network which has incremental IP ID sequencing. Hopefully we have an Nmap script to help us find a computer appropriate to become a zombie. I know the name of the script starts with IPID and put a star now. Here's the script, ipidseq.nse. To use the script, type nmap script ipidseq. And now our IP block, 172.16.99.0/24. To keep it simple, let's scan just the top 2 ports. And here are the results. So let's analyze them. 99.1 is my host system. It's a Mac, and as you see, IPID is randomized. 99.2 is the gateway of my virtual LAN, and yes, it has incremental ID sequencing. It can be used as a zombie system. Good eye. 99.139 is a Linux system. Its IPID sequence is all 0. 99.206 is our target, Metasploitable. 99.222 is our Kali machine. Its IPID sequence is incremental, so it's actually another zombie candidate, but it's already the attacker itself, so it doesn't make sense to use it as a zombie. But I understand you. Yes, it might be fun. But right now, we're going to use 99.2 as the zombie. So here's the Nmap idle scan query. S uppercase I to idle scan. Now put the IP address of the zombie. I want to use my host machine first, which has a randomized IPID sequence. Not necessarily, but I think it's a good habit. PN and N, target system's IP. So as you see, Nmap says the zombie's IPID sequence class is randomized, so we should find another system. So what do you think about using a zombie system with an all zeros IPID sequence class? As you see again, it's just not suitable to be a zombie. Now is the time to use the system which has an incremental IPID sequence class. So again, to keep it quick and simple, I'll just scan the top 3 ports. And yes, scan is completed successfully. To compare the results, I'd like to have a SYN scan in another terminal screen with the same conditions. Ports 23 and 80 are open in both scans. According to SynScan, port 443 is closed. Now we know that the idle scan cannot distinguish the closed port from the filtered port. It flagged port 443 as closed or filtered. So let's run the last query with reason option again. As you see, ports 23 and 80 are flagged as open because IP-ID has changed each time. Since the IP-ID has not changed for port 443, it's flagged as closed or filtered.